Miss Jody here for another video for STEAM physics. We're cruising along here. We're almost finished, and hopefully we can still get together at some point, the end of May, beginning of June, something to finish up our hands-on projects. Kind of hard to do some of that stuff, our engineering and our technology that we had already started, and so I would love to be able to get back together, and I'm really hoping, of course, it'll be optional, but at least we'd have all this work done if we do have the chance to get back together. All right, so continue on in the study of light. Don't forget to be writing your notes on a half sheet, and I'm going to be gluing those in the journals. I'm going to make a drop spot at the front of the Science Center where the dig pits are for you to drop off any of your note sheets and your crafts, anything that goes in the journal, any homework, still having the homework. I think we have obviously BP homework, and then basic physics homework, and then exploring the world of physics homework. And a lot of the technology and the engineering there's not a lot to turn in anymore. We were already done with our engineering packets. We were already done with our technology, champions of science, and champions of invention. So, but if you have anything that needs to be turned in, some of the artwork, if you did any of that, you could drop that off too. Just put it in a baggie with your name on it, and either a Walmart bag or something like that, or a Ziploc bag, just in case it would get wet. And then I'll get that all put into the binders. So that way when we get back together, we'd already be ready with everything, hopefully. All right, so continuing on in our study of light, we've been looking at light and how it has that dual nature, and the idea that it at times really has a lot of wave characteristics, and other times we see it interacting and seeming particle-like, and so that duality and that quantum nature. So now in chapter, I think this is chapter, was that 19? So chapter 20. So chapter 20, now we're taking a look at some of the behavior of light. And so this goes along with, anytime when we study the idea of waves, there are certain characteristics of waves, and there's also certain behaviors of waves. And this is going to go right along with this, because these are going to be behaviors of waves. And so we're really thinking about this particular aspect as light as a wave. Now I know there will be a whole chapter as light as a wave. Next chapter is lenses and instruments, and then the chapter after that is looking at light as a wave again, and that's when they do, explain more the double slit experiment and James Young experiment and all that, which we've already kind of begun talking about. So we will continue this topic, but in specific, the way that waves behave in looking at light with that particular behavior. So one of the wave behaviors is reflection, and another one is refraction. So reflection and refraction. So reflection, the change in direction of a wave at a boundary between two different media, so that the wave moves back into the medium it came from. So this is a very simple idea. The wave is going to be moving in, and this is just my drawing of a wave here. So it's going to be moving in, but instead of moving past the boundary and going into the new medium, it will then reflect and move back into the medium that it actually came from. So you see, so that the wave moves back into the medium it came from. Now with reflection, you're very familiar with this idea, I'm sure, because light's reflecting all the time, and we can use mirrors and all that kind of stuff. Now there's some rules and laws that go along with reflection. And so the laws of reflection, three main things we'll be focusing on in the laws of reflection. The term incident ray, that's the ray that's coming in and making what I would say the incident. It's the, we're following this wave behavior. So a wave comes in, hits the boundary of the medium between this one and the one underneath it, whatever it was trying to move through. But instead of moving through it, so say this was a glass mirror, it then gets reflected back. And so you have the reflected ray. So you have the incident ray, the reflected ray, and then you have what's called the normal. And the normal is going to help us with measuring the angles. It's this imaginary line down the middle that's going to help us figure out the angle side of reflection and even refraction too. Okay, so if you look at this diagram here, I had to put a book underneath here because my book is getting so big on one side opposed to the other. So the diagram that I sent you is going to have these little diagrams here for us to work through. And this one is showing us one of the main aspects of the law of reflection. Okay, so in my orange here, well, first of all, yellow is the light coming in. So the light comes in, hits the plane mirror, and bounces off, right? Reflects off. Okay, so as it's coming in, the orange is my incident ray. Okay, well, no, I'm sorry, just the yellow is my incident ray. But this orange line that I've made here, this is mapping out my angle of incidence. So angle of incidence is the angle that the beam made as it hit the plane mirror and then reflected off, the angle it made with the normal, the imaginary line we put here. So that angle of incidence, if I would measure it, my angle would be A to B to N, and this particular angle we would measure it at 45 degrees. Okay, and then the reflected ray, that's the one that goes from B to C here, and it reflects up. It's going to make an angle with the normal, and I did this in color-coded in purple. And so I'd have an N to B to C. That particular angle there would be my angle of reflection. And so with the laws of reflection, there's three main kind of things that go with the law of reflection, and I've just made them very simple here instead of writing everything out. The first one is I is equal to R. So what that's saying, the incident ray along with the reflected ray, there's going to be an equal going on here. The angle of incident, 45 degrees, is going to be equal to the angle of reflection. So you see this equaling side of things? So when we look at the first law of reflection, this is always going to be the case. When the light comes in and reflects, whatever this angle is, if it's coming in at 30 degrees or whatever, then the angle of reflection will be at that degree. So they're always going to be equal. And so I is equal to R. And the second point in the laws of reflection is I, N, and R. So I is the incident, R is the reflected, N is the normal. I, N, and R are always going to be on the same plane. And all that's saying is, okay, this line is coming out down here, and the reflection is going to stay on the same plane, as is the N, the normal. It's not going to like come out of the page and go into a different plane of the paper. Okay, so the third one is I and R are on different sides of the normal. I just made this easy for note taking. I put the little dot. That's the normal. I mean, the little dotted line, the invisible line, the normal. So I and R are on different sides of the normal, which is obvious. The reflection doesn't take place of coming down here and then reflecting back on this side of the normal. They're going to be on opposite sides. So I is equal to R. I, N, and R are on the same plane, and I and R are on different sides of the normal. So that's the beginning of the laws of reflection. And so the light's going to behave in a way that it's going to follow the laws of reflection. And then in our reflection world, reflection, we have specular reflection, which is, so a plain flat mirror, pretend like my line right here is a plain flat mirror. Plain flat mirror is equal, or when it reflects, it will reflect evenly. If it's specular reflection, the reflection is going to, because this is so smooth and flat, it has such in a way, it is able to disperse it evenly. But diffuse reflection is when the light hits a non-shiny, uneven surface. So see how the bumps, this is my visual of bumps. And so the light rays coming in are going to be obviously reflecting off at different angles because they're coming in and hitting different areas of the surface. So there's no regularity to this. So you can have reflection that is specular reflection, where it's going to be completely, this perfect evenly, or the lines are coming in and it's uneven with no regularity. It's still a reflection situation. It's just the light's bouncing off of different surfaces because this is not a flat surface. Okay, so also with reflection, there is the image formation. So you've seen in our book how image formation works. So this is a terrible drawing, but you get my point here. These are supposed to be my eyeballs, and that's a little nail. So it gives you a little diagram, and you can look in the book for more details about this, and we can, obviously, this is a concept we've seen before because we understand how mirrors work in a sense that the image formation by the plane of the mirror how it works is it's the same size and the same distance from the original image, or the original thing that's the image is being created by. So if your nail is this far away, then in the mirror it looks as if it's this far away. And so image formation is kind of cool. There's more details in the book, and then maybe I'll link an image formation video on for you, but we'll see how many videos I have, but there's definitely more details in the book on that. Okay, so that is what goes along with reflection, and of course mirrors and how they work. All right, so then there's refraction. So refraction is a change in direction of the wave as a result of it traveling at different speeds through the interface between one medium and another. So all that's saying is, as it's moving in, now in reflection, it's coming down, it hits the boundary of the second medium, but it moves back into the first medium. So it's not actually going into it. But when it comes to refraction, when the light comes in, if it hits an interface of something else that it can't go through as fast, it's going to have a change in speed. So therefore it's going to bend. And so the key points are this: different speeds through different materials. So it bends such that its angle with the normal is less in the material in which it travels more slowly. So that's all it's saying is, okay, so here's my little diagram. A will be my A material it's going through, and then B will be the B material. Okay, so as it's going in, let's say this is air at the top here. So light's going to travel faster through air, and it's kind of the way it works is air is faster, liquid, and then you got, of course, solid, which is going to really be slowing it down at times. So we have it going through air, so it's kind of moving, it's coming in at this angle. This is dotted line is my normal that I've created. This line is the barrier between medium A and medium B. So light comes in at an angle, it hits the barrier and moving into, let's say, water or something, which is going to slow it down. So it'll slow it down a little bit. So as it slows it down, then the angle, the light ray bends, and then you see how this angle is smaller, lesser than this particular angle. So that's the rule. It bends such in a way that its angle with the normal, not the barrier, but the actual normal, is less in the material in which it travels more slowly. So it'll bend towards whatever it travels, whatever's slowing it down, and then it will, that angle as a consequence will be smaller with the normal. And so when you're looking at this, it's a simple. A is speed of light in A. How fast is it traveling? How fast is light traveling in A? And then how fast is light traveling in B? And so this eventually will help us understand what's called the index refraction when we start figuring out the ratio between how light travels in a vacuum versus how light travels in different materials. So we'll come back to that. But anyway, so this little beginning formula, this isn't the one you usually use for calculations, but this beginning formula, they start putting in there. Now this can be hard because whenever we get into like sine theta and all that, this is trigonometry, which a lot of you haven't taken trigonometry, and we're only studying this topic, obviously because of light, and there's a little bit, I think, in the lenses. Let me see how much is in the lens calculation-wise. It doesn't look like they give us too much in the lenses on that, but in that particular area. But because with trigonometry, many of you haven't, it's going to be a little complicated. So I might attach just like what is an introduction video, what is trigonometry or something like that, just so you understand it's all about the triangles and specifically looking at the right triangles with right angles and then trying to calculate the other angles, because this is going to be creating angles. So I don't want to get too much into it because it's not like we're going to be spending a lot of time in math on this concept, because we're at the end of the year and we're basically in math just apply our topics from science a little bit. So what I'll do is I'll just show you how they're breaking it down and then turning it into Snell's law. And then I'll probably post a video to the classroom that shows maybe how you can do it with a specialized calculator. And some of you do have the good calculators that you can work with in math. And so you can actually watch how they put it in on the calculator so you know how to do it, because it's kind of complicated. But at least for beginners, just understand the concept, okay? We're going to just say, I'm just going to make it simple by saying, okay, don't worry about this sine theta, just, okay, first angle. So that's what I'm going to just say, okay? So to make it easy, I'm saying, okay, what is the angle as it's coming in from the first material? And then as it's going into the second material, I'm going to parallel that here with the speed of the first one and the speed of the second one, okay? And then when we look at that calculation, they do a couple in our book, but they don't really give you they don't give you an understanding if you've never taken trigonometry or any of those topics, how to like figure it out with your calculator and everything. But it at least gets us started. But again, once you watch the video, we'll just write this one out. And then once you watch the video on how to do it with your calculator, then I'll put some math ones up there just for practice. And you can see how you can do, and you can attach your answers in the classroom. All right, but with this concept of light traveling through different materials at different speeds, here's my diagram. So let's say I'm going at this, light's coming in, these rays. Now, of course, whenever you see lines, what it's saying is crest and troughs, because they're illustrating this as light in a transverse wave, okay? So it's coming in and it's all going down, and then it begins to hit the second medium. You see how this first one, because the second medium slows him down here, he begins to bend. And as they bend, they maintain their wave-like separations there. Some people give this as an illustration. Some people don't like this illustration, and some people do. They say it's not as really accurate of what's actually happening, but it gives you a better feel for understanding how light will kind of all come and bend together. They say it's like a marching band. A marching band is marching through on the asphalt. Let's say they go on the asphalt, and then they as they're marching, then they get into contact with sand. Say this is sand, which is going to slow your marching down. But as they're marching in, and this guy hits the sand first, so he's going to kind of slow down. So therefore, the other ones, as they start hitting, they turn too. And the whole time they're trying to keep their order, you know, the marching band order where everybody's spread out evenly. And so that would be the light rays coming in and then bending like that. And so that would be refraction, the bending of light. Now, like we were seeing the calculation or the formula on the other page, I rewrote the formula in here and simply trying to illustrate, okay, how we would figure out when it does go through its bend, what's the angle, and, you know, which one's slowing it down, which one's not slowing, you know, whatever. So they give us an example with, they say, okay, here's a diagram. So here's A. So the light's coming in, and as the light's coming in, let me get a highlighter there to keep track of where the light is, since I have all of these pencil marks on here. So light's coming in here, and it bends here because it moved into the second medium. All right. Now, when is coming in, this is opposite of the one we were doing on the other page. This is water, which is slower, and now it's going to move into air, which is faster. So, like it said before, the whichever one slows it down, that's the one that will have the smaller angle. So it doesn't look like it here because it's my bad drawing, but eventually water should have a smaller angle than B, because water is the one that slowed it down. And if I drew that better, it would be more realistic, because this one almost looks bigger than this one. And so that's just my bad drawing. But keep that in mind. Whoever's slowing down is going to have the smaller angle. So like I said before on the other page, it bends such that the angle with the normal is less in the material, which it travels more slowly. Okay, so in this particular one, it's 30-degree angle. So the problem they give us in the book is they say, okay, it's going to go from water into air, which is going to make it faster. And then we know this angle, but we don't know angle A. And so here's your equation here. And so they say, okay, we're going to say, do we know the speed of material A, which is water? So there's a little table in your book, and it tells you that it's 2.25 times 10 to the 8th. And so you write that little in there because you do know it, because it gives you a little chart of how fast light goes through different materials. And so do we know the speed of how fast it goes through air? Yeah, 3.0 times 10 to the 8th. very similar to its speed in a vacuum, but obviously this calculation isn't super precise because it's just a little bit less in if you showed more signs of precision, but on average, so it's about the same as the regular speed of light in a vacuum. So it's going slower in here, going faster in here. We know this angle, which is this one, sine beta of the B material, and then we just don't know A. So what would we do? So we rewrite it. We don't know this guy. We do know this one. We put the 30 degree in there, and then we know this, and we know that. And so all we do is do our algebra calculations. Now, the reason it gets hard is we have to have that specialized calculator to get the degree into a usable unit here. And so with our calculations with the sine theta. So like I said, I'll attach a video on that so you can actually see how I don't actually have a calculator with me. And if you don't have a calculator, not one of those calculators, I should say, you can, I think there's an online version of one that you can use, and the video will actually show you how to type it in so that you get it correct and you can do a couple practice. But this also then gets us with the calculator into the inverse sine function. It's just complicated. So do what you can. Some of you that have already taken trigonometry, it'd be easy for you. And then those of you that haven't, just kind of get the concept down. Watch the videos. It's okay if you don't understand all the concepts because it's just introducing you to them at this level. Okay. So this 30 degree is going to, with our calculator, is going to be turned into 0.5. Okay. So again, we watch the video for that. And then once we have that 0.5, so that we're all in the same world here and not using degree and then regular numbers and decimals and all that kind of stuff, then I can put 0.5 on this side, 0.5 over 1. That's so I can eliminate this on this side because I just want to get this by itself, obviously. And then I have to also put that 0.5 multiplication over here and just regular algebra functions, and then that way it's over here and this guy's by itself, and then I multiply these two and it goes 0.375, and then I'd have to put that back into the degree form to get my degree, and then I would have it as 22. So it would work with the fact that my terrible drawing, of course, if I put 22 degree here. Remember I said whichever one slows it down, the angle is going to be smaller. So see, 22 degree angle, 30 degree angle with the normal, because that one was faster. So there it is. And this is not normally how you would, well, you would calculate this every now and then with this formula, but most of the time they will take this concept and put it into another formula, which is called Snell's law, using what's called the index refraction. So the index refraction of a material is the ratio of the speed of light in a vacuum, which we're used to the letter C as the constant, to the speed of light in that material. So all it is, it's not a unit, it's a ratio. It doesn't have a unit measurement with it. It's just noted, so N for the index refraction of A. So I think N is for number, but I could be wrong on that, why they use N for index refraction, but it's always used. So the index refraction of A. So what's this new way of looking at it? Instead of all of these calculations between this speed and that speed and all that, you take the speed of light in a vacuum compared to the material, the speed it goes through the material, like water. Okay, and so the speed of light in a vacuum and the speed in the material in this division here will be equal to the index refraction. So then it makes it into kind of a smaller number to work with. Okay, so we have an index refraction for air is 1.003. And then eventually these index refractions are put on charts, and all you have to do is look them up. So you don't have to do all this every time and all that. You just take the index refraction and you put it into Snell's law, and this will help you with calculating your angles of how the light bends. Water is 1.33, okay, for its index refraction. You also use this index refraction in microbiology when you start figuring out, who has a similar index refraction when it comes to how you can see the microorganisms. If you have something that has a similar, and you'll see in one of the videos I post, I think maybe in technology, some of the experiments, some things have similar index refractions. And then, so if they're together, because they're very similar, you really can't see a separation between the two. And you'll see, I think in the one video where they have a little glass put in another glass, and then they think they pour a certain oil that has an index refraction, and the little glass disappears. So that's kind of cool. And so anyways, that concept, taking what we were doing here with understanding this and putting this into the Snell's law. Now, our book doesn't call it Snell's law. Probably don't want you to get too into it because it's kind of complicated, but hopefully with a video it will help us understand this. So Na, the index refraction of the first material, times the sine theta of A, which is going to be my angle figuring out, is equal to the index refraction of material B multiplied by sine theta B, and that's going to be my angle, figuring out my angle. So I can figure these out and they become equal in the Snell's law side of things. So again, we'll look at that with a quick video, and don't get too, frustrated with it. It's complicated. Okay, and then last but not least, we have dispersion. Now, dispersion is another behavior here that's going to be happening with light and waves. Okay, so dispersion is when all frequencies of light do not travel at the same speed in all materials. Up to this point, we're just looking at light as like a big bulk. But we have to remember, light is not a big bulk. Light is separated among different frequencies and different wavelengths. And we studied that before when we studied electromagnetic spectrum. So when you look at the electromagnetic spectrum, you have in the category called light. It's all of them. It's radio, microwave, infrared, visible light, UV, X-ray, gamma. They're all in there. And they're all traveling at different speeds we have different wavelengths and different frequencies, and we know how that's all brought together in the wave equation. So they're not all coming at you at that same speed. So what you have to realize is that when light is coming, there will be times when it can be spread out and separated. And so dispersion is when there's a separation of white light into colors by refraction, by the bending of it. And the reason it bends is because the speed of lower frequencies is greater than the speed of higher frequencies. So what that means is, obviously, let's just negate the whole non-visible spectrum. Let's just look at visible light. When it comes to visible light, the red R is going to be moving faster because it's lower frequencies. And remember, frequencies lower, how much is frequently hitting you. So if it's not hitting you that much, it's lower frequency, and it's going to actually move faster than the higher frequency light, like violet. So most of the time when they talk about dispersion, they'll just use these two colors, red and purple or violet, so that you understand they're all going to be moving different speeds, but they're going to say the speed between this, the speed between that. You could see a big difference in a sense when it comes to dispersion. So how that works is, one, rainbows are built on dispersion and light traveling at different speeds, different frequencies of light. But also the prism experiments back in the day with Isaac Newton and all them. Okay, so the white light comes in, and as it comes in, red, who is going to get there faster, begins its first bend, right? Because it's going to go through a different material. So it's going to bend, and then it's going to bend to come back out. And then orange, and then yellow, and then green, but purple or violet, being slower, gets there a little bit later, and its speed is slower. And so therefore it's even slower in the new medium. So there's a bending and a separation of the colors as it moves through the prism. And so when that prism becomes that second medium, the light is dispersed. And that dispersion you can see in the rainbow, the visible light spectrum that comes out of the prism. Same thing is going to happen in the rainbow world. And so with the rainbow, let's say if we have this A, which is going to be my white light. Of course, I made it yellow, but you get it. And so my white light's coming in. It hits the rainbow, which is going to be the second medium that is going to slow it down because it's coming from air into water. So it's going to come and it's going to bend the red light. Then the red light's going to hit here, reflect out, or do a reflection, which the angle isn't perfect here, but you get it. It would be. We would have the law of refraction, I is equal to R on that. But then it would reflect off of here, and then it would hit here and then come back out here. Now, by the time purple gets here, which is slower, violet, then it bends differently because it's slower. It hits here, and then it reflects back, and then it bends again and goes here. So therefore, red, between red and violet, which still is also oranges in there, yellows in there, greens in there, blues in there, right? I just didn't draw them all in there. There's going to be a dispersion. So this is the effect that happens with a raindrop, but imagine if you have multiple raindrops, that's where you get that rainbow formation. So that rainbow formation, this is my bad drawing of here I am, and same thing, the white light, let's say this white light, the first ray here, of course there'd be tons of rays all at the same time and tons of water, but just for an illustration of 2 water droplets. So this ray comes in, hits the water, does this, and then my red bends out down here towards the bottom. I'm standing here. Is violet still bending out here? Yeah, violet's still bending out here, but I'm down here. So what I catch is the red in my eye. Now, this particular droplet, which is lower as it comes in, red comes down here, which I don't see very well because my eyes are all the way up here and when I'm looking all in one area, but the violet of this drop hits here. So I begin to start having this layering in the sky, which creates the rainbow effects. And so I'm going to send you a video that gives more detail because it's not just 1 or 2 droplets. You can see in my diagram here that I gave you. This diagram isn't for us to find the complex angles or anything like this. I just like this one because it looked like it was showing us how many raindrops were in the sky. And so you can use this for the video on rainbow formation so you can understand, because it's not just the regular rainbows. There's the inverse rainbows, how do those form? And it's just pretty interesting, this whole rainbow concept of the dispersion of light. So the dispersion of light creates rainbows. And then on this one, we have also this diagram, which is the atmospheric refraction. So the atmosphere will cause bending because as the light is coming in, it's hitting a second, or it's hitting the boundary of a second medium. And so traveling from here through, not hitting the atmosphere yet, and then traveling and hitting the atmosphere, and then it's gonna do a bending. But then also, depending on where you're at, the angle, when the light comes in up and down vertically to you, or when it comes in at an angle, you're going to have different colors going on. So this is why we have the sunsets that are really cool with all these cool colors. And so I'm attaching a video on atmospheric refraction for you so you can get an idea. And then there's also the last concept, which is total internal reflection. So total internal reflection, this is an easy concept in the sense that when you have light coming in, hitting a second boundary, so let's say glass to air, so we know air is going to be faster. So see, my angle's 30 degree here because it's slowing it down, 50 degree here. So, and the angle goes with the normal. You always have to calculate it with the normal, which is that pretend dotted line. So my glass is slower, and then it hits air and it gets faster, okay? So if it comes in at this angle, then this is my angle in air, already calculated for us. If it comes in at 35 degree, here's my angle 60. If it comes into at 40 degree, my angle is 78. And so we can do these calculations. There eventually comes a point. This one's 41 and this angle is 86, depending on, and this is terrible drawing because they're all basically, I've drawn them all at the same angle. But you get what I'm saying. If the angle's bigger here, then this is going to be bigger here. And so, but there comes a point when there's an angle at which the light hits that it no longer, see how it's down, going in, then eventually it gets to a point where it doesn't go in. Instead it goes in, it reflects back. And that's what we call total internal reflection. And this is total internal reflection is how mirages form. It's how we use how we create the fiber optic cables that run so many things in technology, our internet as a whole. I'm adding some videos to your technology on the fiber optics, how they work, so you can understand that concept of total internal reflection, and then also then how the fiber optics have linked us together worldwide through the World Wide Web. And that's pretty cool information. I think that's in technology. I think it's in technology, or engineering, but I think it's technology. No, no, no. It is engineering. I'm sorry. It is engineering because technology. I did a lot of the experiments that can go along with reflection and refraction and dispersion for you to try at home. A couple of them, if there's any that you can do, and send me pictures. All right. But anyway, with this total internal reflection, with the video on Mirage, you can do the information down here. That's why I kind of made this bigger and blank here, so you can draw out a picture of a Mirage and understand how that works with total internal reflection. All right, so that's pretty much it. So just those three concepts: reflection, refraction, and dispersion. And then that's the whole chapter for this one, surprisingly. And rainbow formation, all that, mirages, all that goes with it. But next one, it will be lenses and instruments. And then after that, like I said, light as a wave, and then color. So we only have 3 more. And hopefully we'll just keep going and we can get back together and do some stuff. We'll see. But I miss you guys a lot, and I hope you're doing well.